Thank you very much for being invited to give this talk at Wytham, which I think is extremely important. It's important for us, but it's also important for ecologists as a whole, because it has been the notion better that evolution can solve everything. Evolution, it has been, some people are claiming that things are changing, everything has changed as long as there has been an Earth. What's the problem? Species will adapt. They will be there as long as we are there. That's a very, very dangerous statement. Even worse, that some people think to believe in it. What I am trying to do now is that in some way I will try to take down the talk that this Christian started with into practical applications. I will try to show how some of these very general problems that he addressed earlier today actually has some very big scientific challenges. So what I will say, the answer to my question is yes, but I don't know how. And I will try to enlighten you about some of the problems we are really facing by trying to integrate ecology and evolution. There are some conceptual issues here that is problematic. It is some practical, methodological changes that are important. And there is some interpretational challenges that are important to resolve. So that's very important to have in mind, because this is getting a very, very popular field of research these days. You can hardly open a journal without seeing papers on this mixing between evolution and ecology. And recently, even books has been published on this topic. So it's really important, both in practice and for us as scientists. So my premise is that out there is an enormous amount of variation in population variability, both within species and among species. This is a signal of ecology. And my topic here today is actually trying to convince you that accounting for this population variability in some way can be a predictor of how we can see evolution are facing environmental change. I'm not going into complicated species like Hanna did earlier today. I'm sticking with birds and mammals, which I think is very interesting species because they are so simple. And one of the things that are evidence from those species is that there is a huge amount of variability even among those dull creatures. And if you look at time series of exactly the same length, you will see that the coefficient of variation can range from near zero up to 50 to 60%. So this is a signal of the population dynamics. So my aim here today is trying to relate this to evolutionary processes. So what I'm actually arguing, the argument is simple. Look at the time series here. What I will try to argue that there may be a fitness consequence for an individual of facing a low population size versus a high population size. And I would like you to try to introduce you to some sort of conceptual issues that such a focus will challenge us with. And this is actually a very old problem. If you if you go back to the mid-40s, in the last century, you have some of these sketches you find in the book by Gerald Simpson, The Tempo and Mode in Evolution. That's a fantastic book, by the way. He had no formal background, but still he was able to see what people has strived to model for decades. This is time. This is the evolutionary rate of size. He argued that this is the size of the population. This is the rate of evolutionary change. And he argued that during period with large evolutionary changes, their population necessarily became small. So he really addressed this relationship with population dynamics and rate of evolutionary change. The good thing, why I'm really driving this idea, is that we actually know, I think. That's at least, I think we know some of the basic processes that drives population dynamics. And as Nils Christian indicated in the beginning, it's of course strength of density regulation, but that's why I'm giving this talk, is of course there are stochastic effects. These stochastic effects, this randomness that enters the population dynamics, if you are going to have some sort of predictive power evolution, you really need to address those stochastic effects there as well. And then there is this terrible thing that affects us all, age. And age also is important to include. So what I will start with is some sort of conceptual issues. What is fitness? Fitness means that some does it better than others. In what way? That's the contribution of an individual to the next time step or the next generation. And it's the contribution in terms of genetic matter or individuals. That's why we are sticking to vertebrates, because then it becomes much more simpler than some of the some of the creatures that Hanna was talking about earlier today. And that is that in vertebrates, individual fitness of a female is equal to the number of offspring recruited to the next step, plus 1 if she survives herself. Very simple definition. That means that if you have time series that we have in birds, take 5 years in the little wood outside Oxford in Wytham, where they have studied great tits since the mid of the last century, you get this annual variation in how females are contributing. So, some are contributing 0, some are contributing 5. It's a huge difference. And this mean is varying between year. You don't see it here as well as you should. That's the environment variance. There is also an individual variance each year. That is demographic variance. That means that there is random effect among you, among the great tits, among everyone, in how well you are contributing to the next generation, independent of the number of individuals and the environment. That's demographic stochasticity. And the idea I'm driving now, that is this individual variation in fitness is directly related to population growth. Because the population size at time t, that's the number we started with. That's the mean individual fitness that year, times the second year, the third year, and so on. That really makes what you do as an individual in terms of fitness to have a consequence on the population growth rate, of course, in Norway or somewhere else. That means that the average growth of the population that you are a part of and other species are a part of, that's the difference between what you end at a logarithmic style divided by the time between. And that is the logarithmic, that's the log of the mean fitness. Log where Vg is the geometric fitness. So it's a direct link between what an individual do and its effect on the population growth. How does that really translate into practice? Here we have a phenotype, because in the previous relationship there was no phenotype. Everyone was alike, no fitness differences. Here we have the phenotype. At a different phenotype, you have two individuals. What you see is that on average, they will have this relationship between fitness and phenotype. But what you see, you have an individual variation among individuals having the same phenotype. That's caused by demographic stochasticity. What about environmental stochasticity then? That line is this one. What you see, this is the environmental stochasticity. This is the relationship between the individual fitness and the phenotype differing between years. So there is that means is that your effect on the population growth can be partitioning into a demographic stochastic component and an environmental stochastic component that depends on your phenotype. Now we are starting to see where I'm going. Maybe someone is that because that there is a link between what phenotype you have, how many offspring you produce, and the population dynamics. Then we are going back to those old guys that were mentioned earlier today. The first homage we are going to that guy Fisher is this one. We would like to address that, suggest, propose, or what you call it, that one of the fitness measure that Fisher's introduced was that Malthusian parameter. And the Malthusian parameter is the mean growth rate at a logarithmic scale of a hypothetical population of individuals at a specific population size with a given phenotype and a genotype. That links your contribution to the population growth. And what we do is that we replicate this for different phenotypes. That's one. Then we have these damn problems of age. We know that a lot of the things we record in nature is dependent on the age of this, as Hannah told us yesterday, those simple creatures like sparrowhawks, colored flycatcher, very different life history, but we see these differences in different demographic traits dependent on age. The other thing that we are going to go back to Fisher about is that he also introduced to us a second important concept. That's the total reproductive value of the population, which is actually the sum of the reproductive values of all individuals in the population. That has an advantage, is that the use of the total reproductive values allows us to approximate population fluctuations of age-structured population with a white noise diffusion process that is not inflated by variation in age distribution. To say it in I started to say Norwegian, but I mean turn to English, is that this means that we can account for fluctuations in population that is caused by fluctuation in the age distribution. That's a very important thing, because then we can have a much better faith in what we are recording. Then we can define the individual reproductive value. That's the stochastic contribution of an individual to the total reproductive value of the population. This is actually then a fitness concept for an age-structured population. Now you see where we're starting. Now we are going from this simple measure of fitness over to a fitness definition that can be applied to age-structured populations. So that we will do then is that we will decompose selection into components due to their effects on the total reproductive value of the population. So this is, no, it's really, yeah, we can jump there. This is, what we have done is that we have computed the total reproductive value for a lot of species. What this means is that we can see whether we can find, because what we are going to do soon, we're going to be trying to understand how this pattern in the population dynamics affect evolution and selection. And what we see is that if we calculate at which age 50% of the total contribution of an individual occur to the population growth rate and correct for generation time, you see some very clear pattern across species that can be explained by life history variation. So if you look at this graph, this is how this is how, if this is generation time, this is different species of birds and mammals. If each life stage has contributed equally to the total reproductive value of the population, then you would have a slope of 1. What you see at the contribution to the population growth, the longer an animal or a bird live, the larger proportion of younger ages affect the are explained by variation among the youngest age classes. That has also, this one is significantly different. The same pattern we see also in demographic stochasticity. The major part of the demographic stochasticity you see in long-lived species is caused by variation around age classes close to age of maturity. But environmental stochasticity, that line is not different from 1, even taking away this one. It shows that the environmental stochasticity affect every stage of the life cycle equally, and that doesn't different with the average generation time of the species. What does that mean? It does mean something about where selection is likely to be more effectful. So, to summarize now, we have now concepts that relate individual fitness to population growth. We have a method that can be used to study species with a very different life cycle. And we have some sort of concept how to relate those two things. So what does that implies. There is some critical age classes for population size that is formed around age of maturity, especially in long-lived species. This population will be particularly vulnerable to demographic changes in those age classes. Then, going to evolution. There we have some more problem with age. One of those problems is that selection episodes are not independent. What you experience as an adult is dependent on what you have experienced at younger ages. That creates an autocorrelation in the selection process. We see that fitness is difficult to define, but we have shown you an approach. We have famous papers written by famous people how to do this in populations where there is no stochasticity. But we know if we are going to have a predictable power in evolution, we have to account for climate change, environmental stochasticity, for instance, driven by climate change. How do we do that? We have developed a set of methods for dealing with evolution and selection age in age-dependent population. What is the key is that we are taking the concepts that we are used to describe the population dynamics into account. Going back to Fisher, in some way scaling the contributions of the individuals by their reproductive values. What does that mean? That means that we have 3 levels of stochasticity. That means that, as we have seen, stochastic environment influence mean vital rates. The optimal age-specific phenotype fluctuates among years because of temporal variation in the environment. And third, then the phenotype of an individual is not constant. It's also subject to stochastic environmental variation generated with by plasticity. How are we going to generate this into a common context? We start within one age class. What you see here is that you have the characters. This is different. Here you have the phenotype. Here you have survival. Here you have fecundity. What you see is that these components affect the reproductive value. That means that these 2 fitness components can be added and related to how they affect the reproductive value. Then we can do this. This was the previous red line. Then we can combine that again across age classes, again finding the value that gives the highest contribution to the total reproductive value. That means the value that are selected for. But then there is fluctuations in the environment. That actually is the variance in the height of these peaks. That means that we can go from a phenotypic induced variation in one fitness component at one age class to an effect on the dynamics in the end. That meaning that we really can vary the ecological and we can relate ecological dynamics with evolutionary processes. Then we have this famous Robertson price equation. We can do the same as that. That's so simple. That is unbelievable, but that is useful. What you have is that you have the change in the mean character from one time step to another. That is actually the sum of the selection plus a transmission term that can be from one generation to another, which can be caused by heritability, maternal effect, and whatsoever. What we have done is that we have extended that equation to include age structure. Because in an age structure population, this selection differential is difficult to define because the contribution of a given phenotype is dependent on the individual age, as you have seen. And what I'm going to demonstrate to you, this is a very simple organism. This is the house sparrow. What we can do is that we can partitioning the selection on different phenotypic traits, like the, for instance, body mass, tarsus length, into different ages. Use this conceptual framework that we were presenting in graphs to look at selection and how that will affect the total selection acting on the population. And what we are looking at is two very important traits. That's the fledgling body mass and the tarsus length. What you see here is something very disturbing. Here you have body mass. Here you have different way, in the traditional way of calculating this selection in different years. What you see is that this selection on these two characters seem to vary a lot between years. However, if you account for this damn fluctuation in age distribution, much of this fluctuation, at least in body mass, is away. It still remains in tarsus length. This really shows the importance of accounting for age-specific variation, even in a species where there is not so much age dependency as you have in many other species. The other thing is that you have to account for demographic stochasticity. This is random variation in reproductive success and survival, as I've told you repeatedly. In the population dynamics, it really affects mostly small populations. But in selection, it will also, in selection studies, it will also affect this, what you will be estimating, because it introduces random variation in who is getting successful or not. So you have to account for that. And if you account for that, you will see that you need tremendous power in order to affect significant selection. You see, if the demographic stochasticity are increasing from 0.2 to 1, your power are dramatically reduced. So this is, you cannot do selection studies in natural population without having some sort of assessment of the effect of demographic stochasticity. Then we can do a preliminary summary. The good thing with what we have done is that we have some sort of conceptual framework that operates in the same terms as the framework we have for looking at evolution and selection in models without age structure. Demographic stochasticity may bias estimates of selection even in infinite population. And the uncertainties, it's very boring to talk about those things, but the uncertainties in parameter estimates, they are often extremely large. Then we have to be a little bit more optimistic, a little bit more positive. We're going to northern Norway to look at the moose, where we have a moose system at the island of Vega, where some creatures like those come swinging out in 85. We have followed them ever since. Every individual is radio colored now, also with the GPS center, so that they have not so many secrets. we know their sexual life, or at least the outcome of their sexual life. What we then can do is that we can look at selection, and we can look at what something is neglected, that what we do with population, that it may have a potential significant effect. This is the reproductive value. It's extremely high because it's a very good area. Northern Norway is generally a good area. It's have a high growth rate, quite a high demographic variance, almost no environmental variance. It's what we are looking at is the combined effect of selection on body mass and birth rate. Because you know when it's getting warmer, the moose and ungulate should be given birth at earlier age in order to have this spring flush of good vegetation that appears at an earlier stage. That means that it is selection for natural sexual selection for early birth. Early birth in general give higher body mass, but those damn creatures, they are shot. How does that affect selection? What we see is what we would expect. The weather is getting warmer and the birth rate is getting it's getting later. So that's not what we should expect. What's happening? That's because we get selection against birth rate. And we get selection against body mass. What has happened? In males, we get the same selection against early birth, contrary to what we expect. What's going on? That's due to harvest. Twin mothers at this island are generally heavier and older. That means that there is a higher probability of losing a calf among twin mothers. That means that small single calves are favored. That means that those that are born late are favored, contrary to what you expect as an adaptation to climate change. Also, we know that these things are heritable. And what we see is that in males, we get a significant effect of having later birth. We have a significant effect of getting a little bit larger in males. But what we see is that we get a selection against body mass in females. And the larger a female is, the more calves she produces. So what the hunters do is getting a selection pressure that prevents adaptation. Then everything I've talked about now has been very simple. No density dependence, a little bit complication with age, but that's a very, very poor theory that cannot account for density dependence. And what we will argue is that RNK selection that has some, it's not even taught these days in many courses in evolution. And that organizes back to MacArthur and Milson in '67. And that says that when you have RNK selection, that's density-dependent selection. But there is a trade-off, so that those phenotypes doing best at small population size are having a disadvantage at large population size. That may occur, but at this moment, take that for granted. What does that mean? Already MacArthur in '62 showed that it has some profound conceptual consequences.
What does that mean? That is that this is not the specific growth rate that are maximal, not your number of offspring, but it's the carrying capacity, the population numbers that are going to be maximized. So the simple graph here showing that you will have selection towards K1, not the largest growth rate. Oi, something has happened. This is a very, very simple expression, because this means that it is not the mean individual fitness that are maximized, but there is something else. And what we have shown, that is this, there is other maximation criteria, which is the expected mean population size under density beds that are maximized, not the mean fitness. So if you look at what we were going to propose as a general fitness measure, what is the Malthusian fitness? This is the Malthusian fitness. That is the mean, the growth rate of a population size, of a mean phenotype at a given population size. It's the same definition as for the density-independent population. It's the same definition as Fisher tried for the age structure population. It's a general measure of fitness. But that's not the fitness that is maximized in the density population. That's what's maximized is this function. So here it's a little bit clearer. Let's say if you have no demographic stochasticity, this is 0 in that very nice formula I was showing you. This, what then is maximized is n. In a density-dependent population, that's k. Actually, what MacArthur showed already back in '62. When you have environmental stochasticity, you will get a selection for higher R. You will get R selection. So this, even though it's different equation, different formulas, it's the same concepts we are using. And what you will have is that you will have evolution getting to this value, maximizing that dam function that it was not able to show. But it will be knocked down all the time by environmental stochasticity. So evolution is stochastic. What we also see is that, as I said, increased environmental stochasticity selects for larger R. So now I'm again talking about vague concepts, formulas. Have we any evidence for this? Because one of the things that made R and K selection so unpopular was that this finding of MacArthur and Wilson was overstretched. And people understood that this was overstretched, and then they said that the whole theory was just bullshit. So what we really have to show is that there is R and K selection ongoing in national population. And what does that mean? That means that the fitness of a phenotype should change with population density. That means that there should be an interaction between the character and the population size on the Malthusian fitness. And again, simple questions need simple organisms. So we go to the great hits in the Netherlands. We have individual fitness there, going back in time series back to 47. We are using just data for 55. There is some assumption, but what we find is that we find stabilizing selection of the total number of clutches found produced per female per year. You see that this optimum are decreasing with increasing population size. We also see where the population size, where the selection gradient are going to 0, decreases with population size, increasing population. There is this optimum criteria. That's the clutch size maximizing the fitness function. That's the optimum. We see that there is an interaction. We see that those that lays only 5 eggs, they do much better at large population size than those that produce a high population total clutch size. That means that there is evidence for RNK selection. The heritability of clutch size is 0.12. That means there is potential for evolution. What happened? This is what will happen. You will get fluctuations in the breeding values for clutch size over time, but the density-dependent selection, RNK selection, will move this clutch size, these breeding values, through this value that is maximizing the fitness function, causing stasis, causing stabilizing selection, causing no possibility under this assumption for adapting to a changed climate. So that means RNK selection provides a general mechanism for a reciprocal interaction between ecological and evolutionary population in a stochastic environment. They can produce stasis, researching fluctuations of the mean phenotype around that value that maximizes the expected mean population size, not the mean fitness. This implies something. That madness, as you saw with the moose example, where there was no density relation. But many human activities affect population fluctuations, causing the level of the carrying capacity to fluctuate. That will generate selection. That will generate evolution. That means that there is a close interaction with between the population dynamics and evolution. And look at these things. What happens if you harvest? If you harvest, you keep the population down. Just by keeping the population down, you generate a selection pressure for increasing growth rates in a dense regulating population. So the population dynamics that's the conclusion. That's a longer answer than a simple yes. Of course, it took 3/4 of an hour. But the conclusion is population dynamics are a necessity for understanding evolution. Thank you.
Thank you very much for an excellent talk and a small token of appreciation. Thank you. We just have a short break now and we start with a parallel session in 15